for our discussion on transforming decision-making with AI and the DATUM framework. So my name is Jared Smith. I'm a manager at Deloitte. I've been working in the aerospace and defense industry for about a decade now, performing digital engineering and digital transformations for organizations. I'm joined today by John DeHart. John, you want to introduce yourself?
John DeHart. Working? Oh, thank you. Yeah, John DeHart. I work for Avian, system engineer, been in the industry for about 35 years, too long. But moving over to the AI stuff because it's fun.
Okay. So if you missed the last conversation, we made a very compelling argument why making good decisions driven by data is the future that our organization is headed into. What we are talking about today is how making data-driven decisions is dramatically being improved by integrating artificial intelligence and LLM solutions. That's what John and I have been up to primarily for the last few months, and it has been a wild journey. So that's what we'll talk about today, is a little bit about that journey and what we've come up with thus far. So we'll start with just a description about how decisions are made today, and then we will talk through what AI augmented decision making it looks like now and what it looks like when it's being brought all together. We've got hopefully a demo, or at least a look at what some of the outputs are that we got from this process. Developing the data. So decision analysis data model, it's a product that's been released as of April by the INCOSE Decision Analysis Working Group. It's a data model that is available, SysML data model available in the INCOSE SE lab. The origins of this decision analysis have been around for a long time, for decades, as an industry, but best practices and are currently captured in textbooks, and most decision analysis are conducted on Excel spreadsheets or written reports. So it's a very document-heavy process, and we recognize that as an opportunity in the working group to move this into the digital age, take advantage of some of the technical digital tools that are available, and improve its adoption and hopefully its integration to support some of the new digital technologies that are on the precipice of being developed back in 2022. Well, that's exploded. Very recently, we released the first version of the DATUM, and it's out in its beta form. We're looking for folks to give us feedback on that, and that's really where John and I joined hands. One of the things that became very clear when we released that initial model was, while we solved a lot of the problems that are still present in the decision analysis, there are still many that exist. I don't know if you've ever been a part of a complex decision analysis or a trade study. I have, and everyone that I've been a part of suffers from one or all of these things. It's labor intensive. It takes a lot of resources and energy to conduct a trade study or an analysis of alternatives. They take a lot of time. They're very time consuming. Take weeks, sometimes months to do one that is thorough and complete. They are susceptible to human error by miscalculations or misunderstandings. They are limited to the subject matter expertise that you have available to. If you've got all the right SMEs in the room, then you're probably making a very good decision. But a lot of SMEs are time constrained. They may not be available at the time, or you've got a limited staff available to you that may not have the experience necessary to inform those decisions. And still, all decisions up to this point really are manually executed. So manually executed, manually documented. It requires people, processes working in concert to execute these complex processes. So this is the lay of the land, even with the decision analysis data model. But this is where the fun started when John and I got together. So John, I'll hand it over to you.
All right, so let me just give you a little history here before I get into this, because this tool set, this AI tool has essentially changed what I do for a living in a period of time that's less than 2 years. I do not do anything the same at all anymore during the daytime. And I'm an old guy that can't remember how to write code. It's okay for the old guys now because you can sit down, it'll write it for you. It's no joke. All day long, I literally instruct these tools as to what to do. They do them. I don't write a line of code, not kidding. So, and the big deal was, just a quick history here, 30-second one. You know, I tested it. When I found this out a couple of years ago, I wrote a couple of papers that came in. INCOSE was one. I had a couple of others with little conferences. I tested it out. I just wanted to see what this was. I tested it out. I used my past experience in building brushless system motors to test it, and it passed the test. I may have biased it back then, talking to it because it's chit chat back then. Now I don't chit chat at all with it. It's API only work, back and forth. It's generating code for me. It's actually saving the files, creating the folders, creating the structure for me. So I'm essentially guiding it as to what I want, and it gives me what I want because I can call. The other one was the fun team difference. So we wanted to make a team. Jared showed me one time a little team of experts, agents, they call them agents, I guess now, that were building some software. Thought it was neat. I went home, sat by the pool, drank a couple of beers, went back inside, made a team of agents have a debate. And it was just, you can give these agents personas, and they debated, and they were fighting. I had to add a moderator. I had to put controls in there. They were skipping each other's turn. I don't know how that was even happening. So it was crazy. So that's the kind of the history behind what's going to happen here. So that was all unstructured. I didn't know what I was doing. I was writing the code myself. I was having some fun learning what this was. And it turned out it's pretty powerful. And the more, I'm still just scratching the surface, I think. I know we are. We're just scratching the surface right now as to what this can do and where to go. But anyway, lessons learned from Datum 1. So I'm a novice to Datum. I'm not a novice to decision making. I'm just a novice to the Datum model. I'm 6 months, 5 minutes, trying to understand how to use it. And this little tool we're going to show you, I can't demo it. Unfortunately, I made a mistake getting prepped here, but it really was the idea was to use the datum as a test case, or really test the datum out in a formal manner with some coding. It turns out something exploded, got really weird. It's going a little bit crazy now as far as how far we think this might go. So datum, one of the things is number one, working on the datum, trying to use it as a test case. 2, it's a SysML model. I like SysML. It's an interesting tool for a specific use case, though. It's really made for architectures, trait studies, traceability. It's not a process model. It's just not made for that. You can't run the models because we can kind of run the models. We use Cameo. But even then, how do you instantiate a model for another agent? How do you make 1,000 models, instantiate 1,000, then run them all? You can't really do that easily. So again, here, this is why, it kind of hooked up with Jerry. We started feeding these little lines, one-liners, and before you know it, we got this stuff. It's like a pipeline. Then give me a one-liner, and I got 6 months of work. So it's not the way I want it. But then, the BPMN came to light. It's like, that is a business processing model. So now we can actually put together these processes. It was really just to show an example of the data model with AI integrated. So just a couple steps, have the OpenAI take some context, make a decision, take some input, do a little bit of learning, have some fun. But then these agents grew. I started understanding how to connect them. I started understanding how to manage the context flow through the process itself. So now I can kind of control. It turns out I can turn off the probabilistic part of this and control what I want and get it out of it. So rather than I'm guessing, chit-chatting, and hoping it gives me a good answer back, I know what I'm going to get out before I even ask it. I know exactly what's going to return, how it's going to return, at least in a test case. So I have these test cases to Data may change. Got to test it again before you really start trying to compete. So that's kind of that's just the history of what's going on here. And this is where we're going with this idea of using artificial intelligence, a team of agents with personas. You define a persona for those agents, tell them system engineer, mechanical engineer, program manager. You tell them what they're supposed to be doing. Give them their knowledge, up front. So they know, here's my knowledge set. That's a proved set of knowledge, not some stuff from searching the web. A proved set of knowledge. Who am I? What do I know? How do I apply it? And when you start doing this task with the beacon in, all of a sudden you can really run these models and for many, many different problem sets and in many different forms. It's not just one form where it's like you ship chop. You got to do exactly the same thing. It's flexible and it can make decisions on its own. What tools, what decisions to make, where to go and flow. So it's just a look. All right, so here's critical. And this is kind of not in the write-up for the class, and the reason why this slide deck doesn't quite match what we wrote up, it's just going too fast. It's like literally this was, when we read this November, and it's like completely gone. Everything we started with, all the ideas we were going to do, they're history. They're literally years behind where we are right now. So the idea of an ontology, it's a very scary word, but it's really not once you learn how to build one. This is an ontology that I use to learn how to make an ontology. Because my original ontologies were a mess. They were a bunch of nodes everywhere, elements, relationships. I didn't understand it. There's a Barry Smith. If anybody's interested in learning how to do this, he has a great video series on YouTube, and it walks you through building ontologies for system engineers. It's great. So this kind of morphed out of that. Essentially, it's just an ontology for conceptualizing a system. So it's a concept, and it seems like so simple. But when you look at the diagram, you're in the same boat with SysML. Now I have a diagram. What do I do with this diagram? How do I use this? How do I execute it? I don't know. That wasn't a thing, but now it is because these are words. These are semantics. So the AI agents can use this here to actually do something with it. Before you had to write a while loop and natural language processing and shove it in there and make sure it's all right. And it's too rigid. It didn't work very well. This is almost free form, and you can allow a system to automatically conceptualize what you're looking for. If you build an ontology and ask the LLM to please talk in this language here, don't use other languages, follow these rules. Your input will look like this and your output will look like this. Please don't deviate. It will deviate, by the way, too, so you got to stay on top of it. Anyway, real quick here. Requirement specifies a component. A component performs a process realizes a function. And really, a big one here is component presents an interface. So now the example is an engine performs combustion. The combustion process realizes thrust. And the thrust is created by an engine. You have to have an engine to generate thrust. So it's kind of a simple little triangle, but you'll see here in a minute, it's like it goes crazy because you execute it. You don't look at it, not a picture, it runs. All right, so here it is. The ontology is in effect. So here, sorry. Is there a way to make this larger? No, you guys can read it, I think. I can't read that. So starting from the bottom, what I did was I extracted requirements from a CDD, which is, capabilities development document from our customer. And I just said, I went through it and said, give me all your requirements out of here. I made those up myself, extracted them myself. And for each one, I ran through a loop with an LLM answering the question, please fill it out, take a guess related to this requirement as to what components that requirement will need to fulfill the requirement. What processes will you need to fulfill that requirement? And what functions will you need to fulfill that requirement? And it estimates those. It puts them in here and guesses at them. So that right there is a graph of the actual requirement. The pink dot is the requirement. This is the graph of the ontology, the one step of the ontology. It can extract the constraint, easily can extract constraints from the requirement. It's not a problem for it. It also can specify what the components should be in gray. So I think this was a heating and keeping the cabin temperature controlled So it's saying, yeah, you got sensors you got to deal with, you got some heating, and cooling conditions. It also finds out what functions and what processes we need to do. And it just takes a guess. It's a first cut guess at it. But I had 435 requirements. So then also, by the way, if I were to take those 435 requirements and I sat down, I'm a pro at this, at least I was a pro, it would take me weeks to lay this out and get the conceptual model done. The conceptual model really is the basis for all the rest of the modeling. If you're working in SysML, you should have a conceptualized model that is your definition set for your block sets. So we don't really do that very often. We just hop in the SysML, start making diagrams like, where are you getting your definitions from? Made them up myself. That's not a good way to go, because you're going to get lost very quickly. So here's what happened 5 minutes later after I pressed that button. That is a conceptualized aircraft right there. You can also see that the requirements are pretty crummy. Half of them aren't even connected to the rest of the aircraft. They don't know where they're supposed to be. They don't know how they hook up to it. So first cut was pretty powerful. And I did that, no joke, in 5 minutes. Press the button. It runs through each requirement and estimates it conceptualizes a doggone aircraft. It's crazy. Blew my mind. And it really started off the whole process of, wow, this is really powerful. What a time saver. It's something I know takes 6 weeks for me. Somebody that's not skilled is going to take 6 months and get it really wrong. So, and this isn't even trained. This was just taking a guess from a generalized model. I did not train this model on what to use, where to go, other than telling it to follow the ontology. I did not give it any kind of knowledge up front.
One of the things too is it takes a reassessment of the requirement and says it evaluates it.
It tells you your requirement stinks. Here's a better requirement language. Improves them for every one. It also knows when you have multiple requirements that are very similar, tells you, hey, these are too close, and you've got to clump them and make them go. So you can go crazy here, but it's a good deal. Also, the ontology, and we'll be done with ontology. I'm running out of time. I guess I'm talking too long, but the ontology is easy. If you keep it simple, it's got to stay simple. When you guys start trying to make one, it's going to look terrible. It's a big mess. Your buddies are going to tell you that's not going to work. It has to be like 6 or 7 blocks per domain. Otherwise, you'll get lost. Can't manage. So, for instance, one of the big problems we have when we conceptualize an aircraft or when we work early stage aircraft development is nobody cares about reliability. Nobody cares about sustainment. And then it becomes too costly to actually build the aircraft. And that happens every stinking aircraft. If I wanted to extend my little ontology to include reliability, here's what it might look like. It's 3 more blocks and 5 more relationships. And now I can have the LLM, while it's doing that first set of work, take that too and take a guess at what it thinks the reliability for that component might be, or what the failure modes for that component. Really, right now, probably just failure modes in the conceptual stage, but just conceptualize the failure modes for it. It literally bootstraps an entire aircraft for you in minutes rather than weeks or months. And you start from not ground zero, you start from a 70% solution, 80% solution in 5 minutes for any, that works not just for airplanes, that works for any system you want to work with that you can use. So that's that for ontology. I'll stop on ontology. It's a lot of work. You're understanding your brain will have to be, I'm sure you guys are way smarter than me. It took me like 6 months to really get from a mess to 6 blocks. So stuff. Like essentially what's going on is here, you stuff the pipe, you're not starting from ground zero if you do this right. You really start with a bootstrap system. It could be any system you want to work with, but the airplanes are tough. We know that. Space vehicles, tough. It's great for space vehicles. Get a solution. Once you're done with the solution, you go back in with your smart guys and you make sure, fix it up, make sure it's right. It's going to be wrong. There's going to be some issues. Go back through. The biggest one though is don't do it once. This is not, right here, that's one run. You got to run that 1,000 times, and then you'll get your clustered aircraft, because you're going to have multiple air vehicle options, and they're going to be conceptualized. An 80% solution, 80% of the solutions are going to be very similar. Another 20 are going to be different, And those are going to pop out. You're going to see those, not just one system. So you can't just be a one shot. You're going to end up with junk. You got to run in a Monte Carlo-like fashion. The big deal, though, is when I say control, test, and validate your context, that means you build an ontology and you make sure it conforms to your ontology. I even talk in JSON files. I don't talk in chit chatting. So the input's a JSON, the output's a JSON. You ask the LLM, please only speak in this JSON format and answer per my ontology. Do not deviate. All right, that's it. So then once we got through this first stage here, and work, all of a sudden it comes, well, I got this datum problem. SysML, we did it in SysML, but we can't run it. How do we do this? Have you looked at BPMN, John? I didn't want to look at it. I've got enough with you. And I did go look at it. I'm glad I did because it's perfect for running process. It's made for building and running processes. So it works great, but you've got to have a process of processes. So you build a top level process like your lifecycle model. Then you build all your small processes, integrate them. And now our next step is to bootstrap a whole lifecycle. Go through the whole freaking lifecycle and see how many there are that come out of this. And then as you run your program, number one, you'll have a much better vision as to what the lifecycle might look like, how long it's going to take, and bottlenecks and all this kind of fun stuff. But then you use it as a guide and see where things are failing as you go along. And rebootstrap. It'll be continued. Once you turn it on, it should be running and never stop. You're going to have input coming all the time. It's an event system. Cool. All right, we'll take that. We'll try to put that.
So, what we quickly realized is that we were no longer in the decision analysis space that I was used to, where we are trying to make one decision. We're moving into the real, no kidding, decision management space where now you are managing multiple decisions. You need to understand what events kick off a decision, what events end a decision. You need to understand what decisions are predecessors or successors to the decision at hand. It's really looking at a single decision as a point, and now we're talking about a chain of decisions. We're talking about a fabric of decisions. We're talking about a block of decisions. And how do you analyze that space? How do you store all of that data? How do you query it? Once you start understanding decisions in space, you can also start determining the quality of the decisions that you're making. And you can use your past decisions to inform your future decisions and eventually start improving those decisions using the decisions you've made in the past, understanding what that quality was and helping that to inform your future decisions. So what we're wrapping our head around now is what is this next scale up problem that we're trying to solve, which is no kidding, managing 3D decision space.
That's how you can skip this. So we're putting together an event decision tool. The next one will be a demo. I want to show you real quick. We're out of time. But the idea is this tool is going to be take an event setup where you have an event like a punch, and a punch is coming at you. That's an event. So that starts the decision process. What do? You duck, you fall down, cry, whatever. But you've got to walk through that process. At the end of the decision is another decision. It never stops. You have to keep going once you start it up. It's like an engine. So that's kind of what we were trying to show here. I'll say that when I ran the demo, what I did here was I took an example, selecting a UAS problem. I gave it some information like a requirement set, a specification for all the potential options. And then I gave it instructions on how to perform the analyses. So it had to follow a template on the analyses. Then I go through my little loop up here. That's a DPMN model. So I frame the decision, identify alternatives, evaluate alternatives, and make recommendations. So here's what comes out of it. Where's that? Oh, sorry. So if you that's weird. All right. Well, we click it again. Okay. Here's the output from the model. The models, you can see it's talking to me in JSON files. It's not talking to me in text, although it will break in and out of that. So here's the input. I told it the frame task. Here's my instruction. This is what you've got to do to follow those rules. Here's your decision content. You know, our agency's trying to find the best UAV to solve a problem. And then it says, all right, here's what I think for that first task. It goes through it. When it's done, it makes an actual recommendation. It recommends a particular model, and this is a one-off now. And so I say, well, okay, that's great. Thank you for recommending that model. Here it is. It recommends that particular model. It gives me some justification, tells me why its advantages, key risks, implementation considerations, next steps. This is great, right? It just comes right out on a paper format. Then I say, well, hey, summarize why you made the selection of this UAV. And it tells me why it made that selection. Then I say, well, give me a white paper on this. And it writes me a nice white paper at the very end, and I'm done. So, but I'm not really done. Now I've got to go back and wait. Now I've got to turn on this process that's now waiting for information from the field as to whether that was the right decision, not turn it off. And the white paper is the input. The white paper is the starting point for the actual life cycle of the decision. All right. I think we don't have anything else. Yeah, we're done. Sorry, man. Okay. Yeah. So, yeah, why does it matter? Decision management, it's an emerging problem. You know, it's very complex today, carries greater consequences. We know this is a real problem. We see it on TV all the time. And hey, man, we have no time to do this. It's got to be faster and smarter. And you know, we know Jared said it earlier in the presentation and earlier in the first presentation, it's just a bunch of decisions. It's all you're making is a bunch of decisions. And once you start the first decision, it keeps rolling. It never stops. You can't stop making decisions. All right. No longer solving a single point. We're looking at a space, understanding that the decision space was really complicated. We got a bunch of stuff we're working on that on the side. And the decision interactions and sensitivity is going to be one of our first focuses. All right. Thanks. Worry about me.